This video accompanies the paper Approximating Nash Social Welfare under Rado Valuations. My name is Erin, and this is joint work with Jugal Garg and my advisor Laszlo Vég. So in this video, we are going to be concerned with allocation problems. And here we are given a set of goods or items, G, and our goal is to allocate the set of goods to a set of agents, A, in some manner. And in these allocations, when we give some subset of goods to an agent, she or he will be able to evaluate the subset of goods with the evaluation function. And we will assume that the evaluation function has the following two properties. First, that each agent values the empty set at 0. And second, that the evaluation functions are monotone, meaning that if we give more goods to an agent, he can only be happier. So this is the setting that we will be working with. And we will denote with M, the number of goods that we are allocating, and with N, the number of agents that we are allocating the goods to. And for convenience, we may assume here that the M is at least N. So if you are faced with such a problem to allocate goods to agents, the first thing that you might try to do is to allocate goods to the agents in order to optimize the overall efficiency of these allocations. And this leads you to the social welfare problem. So here, our goal is to allocate this indivisible goods to the agents in order to maximize the sum of all valuations. And obviously the hardness of this problem will depend on the evaluation functions that agents possess. And in particular, suppose that for a moment that the evaluation functions of the agents are additive, meaning that each agent evaluates each good separately and then just take the sum of all the valuations, and that gives you the value of the goods for this agent. And if all agents have additive valuations, then this problem is very easy to solve. Well, namely, for each good, we ask each agent how much they value this good at, and we give the good to the agent that values this good the most. So this is very easy to solve for additive valuations, but then the problems get more complicated as we allow more complicated evaluation functions. In particular, if we allow agents to have submodular valuations, then the problem is NP hard. And in particular, it's been shown that E divided by E minus 1 is an optimal approximation algorithm under value oracle, meaning that each valuation function is given by a value oracle. And moreover, if we assume just that the valuations are subadditive, then there is a two approximation algorithm. This is under demand oracles that we don't need to go into details now. Okay, so this was the social welfare problem, but here there might be a slight issue with this kind of allocation, as we aim for efficiency here, but we really sacrifice on fairness. In particular, here an optimal solution might allocate all of the goods to just one agent, and this will never be a fair solution concept. So then you might try to go the other way and try to achieve a maximal fairness. And this is known as the Santa Claus problem. And here the goal is to, well, let's still allocate the goods to the agents, but instead of maximizing the sum, let us just maximize the least happy agent overall. And this problem turns out to be very hard to deal with. Again, it's NP hard, but here, even with additive valuations, we don't even know if there is a constant factor approximation algorithm. And the best known guarantee here is square root n log n cubed for this problem. So this was fairness, but even this solution concept has another issue. That is that we really sacrifice a lot on efficiency in order to get the fairness. In particular, what might happen in the optimum, that we allocate most of the goods to one very pessimistic agent that is unhappy with everything. And then what we can do is just allocate one of the remaining goods to some other agents. That is one for each of them. And there will be one agent who get lots of the goods. So this is also not an optimal way to do it. So maybe we can try to balance these two approaches, meaning that we try to balance efficiency and the fairness. And this is what the Nash social welfare tries to achieve. So instead of maximizing the sum or maximizing the least happy agent, now we will try to maximize the geometric mean of the valuations. And this geometric mean of the valuations is called Nash social welfare. And in this problem, we want to allocate the goods to maximize the Nash social welfare. So this objective function was introduced in several different concepts. In particular, it was shown by Nash that optimizing such an objective function leads to a unique solution to some kind of bargaining problem. It has been also discovered as a notion of proportional fairness in networking. And also, if we would have such a problem of allocating goods through agents, but instead of having indivisible items, you would have divisible items, then we would, with maximizing Nash social welfare, we would actually recover a notion of competitive equilibrium from equal incomes. So this is how this objective function was introduced. And very nice properties of this is that, as I already mentioned, it offers a natural compromise between fairness and efficiency. It's also scale-free, unlike the previous two questions as we saw. Namely, if you were one of the agents and you try to cheat somehow this problem by multiplying your valuation function, say by 1,000, then this doesn't change the optimal solution, right? Because you would just add 1,000 to your valuation function here, but we can just take it out of the product. And so the set of optimal solution is scale-free. Of course, this is also an NP-hard problem, and we will give a proof for this shortly. So let us show that this problem is NP-hard, and we are going to reduce it from, make a reduction from the subset sum. So let me remind you that the subset sum is the problem where we are given some set of real numbers, and the goal is to decide whether we can partition the set into two sets of A and B, such that the sum of all elements in the one is the same as the sum of all elements in the other one. And this is an NP-hard problem. And let us reduce it to the Nash social welfare problem. And how do we do this? Well, we take our set of real numbers, and for each real number, say J, we will create one good, one item, and we do the same for all of the numbers. And then we create two agents here, and both of the agents value particular good really at the number that this good corresponds to. And then if you think about it, well, because you're trying to maximize geometric mean, if suppose that we have an optimum, and if in the optimum both of these agents get the same value, same total value, then we will have a yes answer to the subset sum problem. If they get slightly different values, so one will have a little less than half and what other one will have a little more than half, then we will have a no instance to the subset sum problem, and thus maximizing Nash social welfare, even here under additive valuation, is NP-hard. Naturally, problem being NP-hard, we'll be interested in finding constant factor approximation algorithm for this problem. And we are not the first people to look at this, and there has been already quite a lot of work along these lines. And the first one was by Colin and Gatsalis, that introduced this very cool notion of pending restricted market equilibrium, which they use to give the first constant factor approximation algorithms. And then it has been followed by a line of work. And I'll mention just a few other approaches. Namely, this is approach, there was an approach building on the real stable polynomials, and the state of the art for additive valuations of with the factor e to the 1 minus over e is achieved by an approach using something called price envy freeness, or some kind of local search if you want. And these three that I mentioned here hold for additive valuations, and they have been extended for some mild generalization of additive valuations. Essentially, you have additive valuations with some additional constraints and factors in the valuation functions. Moving on from this mild generalization of additive valuations, not much has been known until very recently. And last year, or actually, well, this year, Lee and Wondrak gave an constant factor estimation algorithm for this Nash social welfare problem when agents have conic combinations of Rado valuations, which I'll introduce shortly. And how they do this? Well, they extend this approach of real stable polynomials and use some very cool ideas to give this estimation algorithm. I'll repeat again. Essentially, they can only approximate the objective value up to a constant factor, but cannot find an allocation and that does this. And what we give here is really this constant factor approximation algorithm for the Nash social welfare problem when agents have Rado valuations, which I said will be introduced shortly. And we use some matching techniques and some convex programming relaxations to achieve this. Okay, so let me now tell you what are Rado valuations. So each agent I will have Rado valuations, which is specified as follows. So you are, for example, just imagine yourself as an agent, and how will you evaluate a set of goods is using this graph. So these are the goods, and you as an agent have some internal nodes, say, or like some hidden layer of nodes here at T, and there is the bipartite graph between the goods and these hidden nodes here. And additionally, there's a matroid on the set of T. And for a given subset of goods, as indicated here, the value of this set for you is going to be the value, the maximum cost matching M in this graph, such that really this matching only uses the goods that are given. And also the other side of the matching is an independent set in the matroid. Okay, that's a lot of takes. Let's look at some example of Rado evaluations. So first, suppose that there is no matroid essentially, that really every set is independent on this side. So what is then our Rado evaluation? Well, for some subset of goods, it's just the maximum cost matching M that matches the set of goods. And this turns out to be exactly the so-called assignment valuations or OXS valuations. On the other hand, if we simplify the edge set and we still keep the matroid on, so we have the following simple graph. We just have a matching and we have a matroid here. And essentially now the maximum cost of a matching M would be the same as the maximum cost of an independent set in T, which can be translated by the edges also to G with respect to some cost function C. And this turns out to be exactly weighted matroid rank function. So these are two very nice examples of Rado evaluations. And we will give a constant factor approximation algorithm for these evaluations. And let me try to at least illustrate one aspect of why we care about these Rado evaluations and why they are useful for our approach. So this is because for Rado evaluations, we can define we have a very nice description of a concave extension of a function. So recall that really evaluation function is a function that maps any subset of goods to a real number. And this is really a function over unit cube. But in order to work with any kind of concave relaxations and stuff like this, we will need somehow to extend this evaluation function to the whole unit cube, not just the integer points. And for Rado evaluations, there turns out to be a very nice way to do this. So recall that really like Rado evaluation was defined on the subset of goods. And now we can extend it really to the whole unit cube. And for some vector x, the concave extension, this Vx, is going to be defined as essentially the maximum weight fractional matching that uses at most xj of each good j. And a nice thing about this, first of all, this is an extension, meaning that for integer points, we do recover the Rado evaluation. Second nice thing that this is really concave, and this is going to be important for the Nash social welfare problem. And the third nice thing is that, well, we can really solve this linear program in polynomial time. So this concave extension is actually useful, right? Because, for example, for submodular evaluation, this concave extension might exist, but it's actually NP hard to evaluate it. and this is not very useful. But as I'm saying here, for Rado evaluations, we can actually evaluate it. Okay, so this is what Rado evaluations are. You will not need to really understand what they are for the rest of the video here. Sorry. And if you would like to see more details, I will refer you to the paper. So let us now try to give the overall an overview of the algorithm that we use. So recall again, we are interested in maximizing geometric mean, and we are looking for a constant factor approximation algorithm. So obviously the first thing you might try to do here is really to, well, let's try to relax our problem, right? Our aim is to maximize geometric mean. Well, at first, this doesn't look like a convex or concave objective, but if we take a logarithm, then we will have a concave function and we are maximizing it. We have linear constraints, so this is a convex program, so it's all fine. So just asking for relaxation actually makes sense. But the immediate issue is that the relaxation has unbounded integrality gap. And let me just try to illustrate why. Well, we could have some set of goods and we could have one really desirable good that is like a super high value for everybody, and all the rest of the goods are really like worth almost nothing. And then if we look at integer, and all the agents are the same. So if we now look at the relaxed solution, we could just give 1 over n to each of the agents. So everybody will actually get a decent piece of the very valuable good. So they are all happy, and also on the average they'll be happy. While in the integer solution, we can only give the super valuable good to one agent, and everybody gets peanuts. So on average, they're also not very happy. So the integrality gap turns out to be unbounded. So in order to avoid this, somehow circumvent around this unbounded integrality gap, what we use in our approach is mixed integer relaxation. And in what sense? Well, here we will somehow in our approach, we will choose some set of good age, and this set will be assigned throughout the algorithm only integrally, and the rest can be assigned fractionally. So this is exactly what is illustrated here. So we are still maximizing our geometric mean, or if you take the logarithm, then this is convex program. We still have that each good is assigned at most one unit of each good is assigned. And then we just ask that really for this goods age, we allocate them integrally. And again, this is just a relaxation, right? Because we just like relax part of this of our mixed integer program. So this is what our starting point is. And let me try to give you like an overall an overview of how we actually now manage to design an algorithm. So first, I will tell you how do we actually choose this set of goods that will be assigned integrally, and this is important. And then I will tell you, well, we actually don't need to work with this mixed integer program, but then there's a slightly different mixed integer program that is easier to handle and has a bit more structure to it. And then once we do that, I will tell you how to approximate this new mixed integer program. And then we will kind of find sparse solutions to the new mixed integer program. And then finally, we are going to round our solution. So let's start with these 5 phases. Let me tell you first how to find the set age of the goods that we allocate only integrally. And this is done as follows. Well, we are simply going to pick set of goods that maximize Nash social welfare under the assumption that, well, each agent only gets one good. And how can we do this? Well, really each agent will get only one item. So we want to maximize this. So this is the same as maximize the sum of logs. So we can just put on each edge, we can put log of Vij, and then we can find the set age. as the set of items that are matched, set of goods that are matched to agents and by the maximum weight bipartite matching in this graph. So this maximizes exactly the Nash social welfare under the constraint that each agent gets one good. And here I'll point out that this is just the way how we pick set age. And we actually cannot use this matching to allocate the good to agents. And actually, if you do it, then you cannot get a constant factor approximation algorithm. So this is our first step. And now I will move our set age here. So let me now tell you what is this a bit more structured program, right? So in relaxation, we said that we will allocate the goods here fractionally and the goods here integrally. But now I'm adding more structure by asking really that in our mixed integer program, we allocate these goods by matching. And know that this is not really a relaxation anymore, because in the optimum, maybe all of the items were assigned to one agent, but now I'm asking that they are assigned by matching to the agents. This changes the program slightly, but still it's fine because we only lose a factor of 2 times e to 1 over e. And so we can just work with this slightly more structured program. And now let me tell you an idea of how one could try to approximate this program. And what we show here is that we can approximate this this more structured integer program that we called mix plus matching. And how do we do so? Well, first we ignore this set of goods age that have to be allocated integrally. This will really leave us on the other side with some fractional program, which we can solve and find some optimal solution to this restricted fractional program. And then essentially what we do is we assume that each agent gets some fractional part from here, and then we optimally rematch this set age here. And we can show that this is actually a 2 approximation. And this is our third step. And in the fourth step, this is where we really use the power of Rado valuations. Really there we can show that first that there is a sparse fractional solution of the instance on the left. And we use the full power of Rado valuations. And first we show that there's an optimal solution with support at most n plus 2m. And then again, we use that we are working with Rado evaluation to show that we can sparsify this optimal solution y to y prime by solving another LP and getting the support of y prime down to 2n plus m. So now you can think that we almost have a rounded solution, because on this side, we already have something rounded, and here we have 2n plus m edges used. So yeah, we started already rounding the solution, and really then we can round the solution as follows. We say that it suffices really to round this fractional solution y prime on this side arbitrarily, and then by our choice age, that is the matching sigma that we use at the very beginning, and the rematched matching that we use in phase 3, we can combine these two matchings such that whatever you did in the rounding here, we can actually recover enough value for each of the agents such that the final solution is only a constant factor away from the optimum. And this is just like a short overview of what the algorithm does. I invite you to check out the paper for more details. Another nice thing about our algorithm is that it actually works more generally for the asymmetric Nash social welfare. And here, additionally, instead of just maximizing geometric mean, we are maximizing weighted geometric mean of the agent's valuations. And in this case, our algorithm produces 256 gamma cubed approximation algorithm for this asymmetric Nash social welfare, where this gamma is the maximum weight in this product here. And I will just point out that before our result, really not much was known for asymmetric Nash social welfare. And essentially there was off an algorithm for sub-additive valuations, and no better approximation algorithm was known, even in the special case when we have linear valuations and when these like exponents Wi were just 1 or 2. And the algorithm is really the same as I mentioned before. We just need to work out also with the weights, but that makes the notation a bit more cumbersome. And before I finish, I would like to point out that Lee and Wondrak have recently announced a 320 approximation algorithm for the Nash social welfare when agents have submodular valuations. And essentially they are building and extending our approach to get this new amazing result with quite some nice details to it and new ideas. And thank you for the attention. If you would like to see more details, I kindly ask you to check out the paper or send us an email. We'll be happy to help you.